This question is from GATE 2017 question paper, set number 1, and it is worthy of 1 mark question, and the topic is operating system. So coming to the question statement, consider the following CPU processes with arrival times which is given in milliseconds and length of CPU burst also given in milliseconds, which is as given below. So the given state is, so it is given process ID, it is given, arrival time also given, and burst time also given. So arrival time and burst time it is given in milliseconds. Okay. So coming to the rest of question statement, if the preemptive shortest remaining time first scheduling algorithm is used to schedule the processes, then the average waiting time across all processes is dash milliseconds. So this is what the question statement, right? So coming to the explanation for this question, so the given state is, so we have 4 processes here, P1, P2, P3 and P4, and the arrival times are given 0, 3, 5, 6, so 0, 3, 5 and 6, and the burst time I have given 7, 3, 5, 2, 7, 3, 5 and 2. So here what is the scheduling algorithm we are using? Preemptive SRTF, means preemptive SJF. Preemptive SJF, we can also say that it is a preemptive shortest remaining time first scheduling algorithm. So it means that in this algorithm we are getting preemption. So how the preemption can take place? First let us get that idea and then we can start the solution of this question. Okay. So for example, so as it is mentioned that it is SRTF scheduling algorithm, which is shortest remaining time first. Okay. And the preemption, how it happens in this algorithm is, let's say if it is CPU and if it is ready queue, currently on CPU some process P1 is running and just now process P2 is arrived into the ready queue with some burst time. Okay, so currently on CPU process P1 is running with some remaining burst time, and while it is running on CPU, P2 is just arrived into the ready queue with some burst time. So now this burst time and this burst time both can be compared. If the newly arrived process burst time is less than the currently running process burst time. If the newly arrived process burst time is less than the currently running process burst time, then preemption takes place. So this is what the basic idea how to solve this particular question. Okay, right. So the same idea we are going to implement here and we are going to build the Gantt chart for this system. So coming to the Gantt chart. So at 0, only process P1 is arrived and it is allowed to execute till the next arrival. What is the next arrival? 3. So till 3 it is arrived, it is functioned. So then by the 3, this P1 have completed 3 units of execution out of 7 and 4 units of remaining is there. 4 units of remaining burst time is remaining with the P1. By this 3, P2 is arrived into the ready queue which is having burst time 3. So P1 is currently running with 4 burst time. So P1 is currently running with 4 burst time and P2 is arrived just now with 3 burst time. So 3 is less than 4 or not? Yes. So which means that the currently running process burst time is greater than the newly arrived process burst time, or else in other words we can say the newly arrived process burst time is less than the currently running process burst time, so that preemption takes place. Means that this P1 will be added back to the ready queue and this P2 can be handed over to the CPU. This is what the meaning of preemption. So then this P2 will hand over to the CPU. So this P2 will be allowed to execute till 5, next arrival. So by this next arrival, P1 is there in the ready queue with 4 burst time. P2 is currently running with 1 burst time because 3 to 5 means 2 units of execution is over out of 3 units. So that's why still it is having 1 remaining. Okay. Then at 5, P3 is arrived. So P3 is arrived with how much burst time? 5. So the currently running process is 1 and the currently running process is P2 and the newly arrived process is P3. So the currently running process burst time is 1 and the newly arrived process burst time is 5. So the newly arrived process burst time is not less than the currently running process burst time. So that's why no preemption, means that P2 can be continued. So now P2 is continued. So P2 is continued till 6. So by this 6, P1 is there in the ready queue with 4 burst time, P3 is there in the ready queue with the 5 burst time, and at 6 just now P4 is arrived with 2 burst time. So among these 3 running ready queue processes, P4 has lower burst time. So that's why P4 will execute. P4 will hand it over to the CPU. So this P4, since it is a shorter one, it can be completed. So means that till 8 it can be executed. So by 8 in the ready queue, we have process P1 with 4 burst time and we have process P3 with 5 burst time. So among these two, P1 has lower burst time, so that P1 will hand it over to the CPU and it gets executed till 12. So by 12, we are having process P3 with 5 burst time. So since it is the only one process, we can hand over this process to the P3 so that we can hand over this P3 to the CPU so that it gets executed till 17. So this is what respective Gantt chart here. Okay. So now what we need to calculate here, average waiting time we need to calculate. So for that, let's first consider completion time of each process. So P1, it is completed at 12, P2 is completed at 6, P3 it is completed at 17, and P4 is completed at 8. Next. So when the completion time and arrival time both are available, then we can calculate turnaround time. So turnaround time is the time difference between completion time and arrival time. So that completion time minus arrival. So 12 minus 0, 12, 6 minus 3, 3, 17 minus 5, 12, and 8 minus 6, 2. So this is what turnaround time. Next, now we can calculate waiting time. So waiting time is the time difference between turnaround time and burst time. So 12 minus 7, 5, 3 minus 3, 0, 12 minus 5, 7, then 2 minus 2, 2 minus 2, 0. So therefore, average waiting time is equals to, average waiting time is equals to 5 plus 0 plus 7 plus 0 by 4. So 5 plus 7, which is 12, 12 by 4, 3 milliseconds. So 3 milliseconds is the answer for this question. Okay. So average waiting time for this system, when we apply SRTF scheduling algorithm, we are getting 3 milliseconds as the average waiting time. So it is what the answer. Okay. Thank you. This question is from GATE 2017 set 1 paper. Okay. So this question belongs to operating system, and coming to the question statement, threads of a process share option A, global variable but not heap, option B, heap but not global variables, option C, neither global variables nor heap, and option D, both heap and global variables. So according to the question statement, it is mentioned that threads of a process. So since the particular terminology is plural, so means threads of a process, means that a process is having multiple threads, means that we are speaking about multi-threaded process here. So let's recall multi-threaded process diagram. So coming to the multi-threaded process, so here this is what my multi-threaded process. So this is thread 1 and this is thread 2, and this particular portion is code section, and this particular portion is data section, and this is file section. And in multi-threaded process, each thread maintains its own program counter, stack pointer, and register set. So this is my thread 1. So similarly, program counter, stack pointer, and register set. This is my thread 2. Now thread 3, it is having its own program counter, stack pointer, and register set, so that this is my thread 3. So I can say this is called multi-threaded process. Okay, so in connection with this, let's have image of a process. So what is the image of a process? The image of a process contains 4 parts. What are the 4 parts? One is text section, another one is data section, and another one is heap section. And this is stack section, right? So now the question is speaking about global variables and heap. Global variables and heap. So according to the image of a process, the global variables of a process are saved in the data section. So the data section contains global variables of a process. Contains the global variables of a process. Okay, and this data section size is fixed. The data section size is fixed. So here data section we are speaking. So this is what my multi-threaded process, and this is the data section of this process. So this is what the data section of a process. So here it is having global variables. So these are the 3 threads. These are the 3 threads which are belongs to the same process, and they are sharing data part. So this data part contains global variables. Okay. Next, coming to heap section. So this heap section, we are saying that the size is dynamic. The heap section of a process is dynamic, and this heap section also contains global variables. It also contains global variables. So here first, anyway, with respect to a process, whatever the global variables we have, initially those global variables can be saved in the data section. Since this data section size is fixed, then let's suppose my data section size is 10 and I started my process construction with 10 global variables, but with those 10 global variables I am unable to get my desired output. Then I need to initialize some more global variables, but my data section contains only 10 locations. So among the 10, let's say total global variables which I have initialized is 15, but among the 15, 10 are going to saved in the data section, and the remaining 5 are going to saved in the heap section. So heap section and data section both contains global variables. The heap section and data section of a process contains global variables. So since these threads belongs to the same process, compulsory with respect to this process, these threads must share both heap section as well as global variables. Okay, so all the threads must share compulsory both heap section as well as the global variables. Okay, so hence what is the answer for this question is option D. So option D, it is clearly mentioned that both heap and global variables. The global variables are saved in the data section, which is sharing. So these 3 are shared by these 3 threads, means that the data section is getting shared, and this heap section of a process also contains global variables. Okay, so that's why these threads also must share this heap section also. So that's why the answer for this question is option D. Thank you. This question is from GATE 2017 Set 1 question paper, and this question belongs to operating system. So coming to the question statement, recall that Bilardi's anomaly is that the page fault rate may increase as the number of allocated frames increases. Now consider the following statements. Statement 1, random page replacement algorithm, within brackets it is mentioned that where a page chosen at random is replaced suffers from Bilardi's anomaly. Statement 2, LRU page replacement algorithm suffers from Bilardi's anomaly. Which of the following is correct? Option A, S1 is true, S2 is true. Option B, S1 is true and S2 is false. Option C, S1 is false and S2 is true. And option D, S1 is true and S1 is false and S2 also false. So what is the question statement here? So it is mentioned that Bilardi's anomaly. So Bilardi's anomaly. So what is the meaning of Bilardi's anomaly is, So let's consider first some general statement here. The general statement with respect to the page replacement algorithms is, general statement with respect to page replacement algorithms is, whenever the number of page frames are increased, okay, so when we increase number of page frames in memory, then the number of page faults must be decreased. This is what general statement, okay. But coming to the Bilardi's anomaly, what it is saying that even though we increase number of page frames, even though we increase the number of page frames in memory, okay, so sometimes it leads to more number of page faults. So sometimes it leads to increasing the number of page faults. So even we increase the number of page frames in main memory, sometimes it leads to increasing the number of page faults. But here, whenever the number of page frames are increased in the main memory, the number of page faults must be decreased. So this is what the Bilardi's anomaly statement. So according to the statement 1, it is mentioned that, random page replacement algorithm. So what is that terminology we have used is random page replacement algorithm. So if you consider this one, random page replacement algorithm, so to replace a page which is existed in the main memory with some new page, okay, so to replace one page among the existing number of pages in the main memory by a new page which is coming from secondary memory to main memory, we are selecting that particular page for replacement in a random manner. So which means that there is a possibility, according to this random page replacement algorithm, there is a possibility, that is, I can select one page which is arrived into the main memory first for replacement. It is one possibility. So there are so many possibilities. What is the meaning of that particular random page replacement is, there are so many possibilities. I can choose the page which is just now arrived for replacement, or else I can choose a page which is not used for long amount of time period in previously, that is also I can choose. And I can also choose a page which is not going to be used immediately in the future, that is also I can use, that is also I can select. And there is one possibility, that is a page which is arrived into the main memory first, that particular page I can select for replacement using some other new page. So means that in random page replacement algorithm, one possibility is FIFO page replacement. So that FIFO page replacement algorithm is, if we implement that, then only in that case it is suffering with Bilardi's anomaly. So only FIFO page replacement is suffering with Bilardi's anomaly. And it is not always, it is only sometimes. So that's why, so what it is mentioned that random page replacement algorithm suffers from Bilardi's anomaly. Yes, it is true. So statement 1 is true because there is a possibility for first in, first out. The page which is arrived first into the main memory, that can be used for replacement. Okay, so this is what the basic idea behind this FIFO. So with that FIFO only, Bilardi's anomaly is possible. And it is not always, mind that point, it is not always. For some page reference strings only, Bilardi's anomaly can be happened. So that's why we are saying that statement 1 is true. And coming to the statement 2, it is mentioned that LRU, which is least recently used page replacement algorithm, suffers from Bilady's anomaly. No, this is false. So LRU does not suffer from Bilady's anomaly. Only among the page replacement algorithms, only FCFS or else FIFO is the only page replacement algorithm which is suffering from Bilady's anomaly for few page reference strings. Okay, so hence what we are trying to say here is the final key for this question is statement 1 is true and statement 2 is false. Statement 1 is true, statement 2 is false, which is matching with option B. Option B, and this is what Bilady's anomaly statement. Okay, so FCFS is suffering with Bilady's anomaly, but LRU is not suffering from Bilady's anomaly. And FCFS, mind that point once again I am repeating, that is FCFS or FIFO is not always suffering with the Bilady's anomaly, only for with respect to only few page reference strings it is facing Bilady's anomaly. So hence the answer for this question is option B. Statement 1 is true and statement 2 is false. Okay, thank you. This question is from GATE 2017 set number 1 question paper. Coming to the question statement. A multi-thread program P executes with X number of threads and uses Y number of locks for ensuring mutual exclusion while operating on a shared memory locations. All locks in the program are non-reentrant. That is, if a thread holds a lock L, then it cannot reacquire lock L without releasing it. If a thread is unable to acquire a lock, it blocks until the lock becomes available. So the minimum value of X and the minimum value of Y together for which execution of P can result in a deadlock are option A, X equals to 1, Y equals to 2, option B, X equals to 2, Y equals to 1, option C, X is equals to 2 and Y equals to 2, option D, X equals to 1 and Y equals to 1. So here coming to the main important point is non-reentrant. Non-reentrant. So this is what the main point. So it is clearly mentioned that if a thread holds a lock L, then it cannot reacquire lock L without releasing it. Okay, so if a thread holds a lock L, then it cannot reacquire lock L without releasing it. If a thread is unable to acquire a lock, then it blocks until the lock becomes available. So it means that once a thread is releasing a lock, so let's say this is my thread, I have only one thread here and I have only one lock here. The number of threads are 1 and the number of locks are 1. Okay, so if this thread currently it holds this particular lock, after holding this particular lock, after using this, it is going to release this lock. Yes or no? Yes. So it is releasing it. So once it is released, again if it wants to acquire this lock, is it allowed? No. That is what non-reentrant meaning. So once it releases this lock, again it can't hold that particular lock. So since it is unable to acquire that particular lock, then what this thread will do? This thread will block itself until the lock is available. So it means that for X equals to 1 and for X equals to 1 and for Y equals to 1 only, there is a deadlock is possible. Reason? Once this thread locks this, once this thread release the lock, again it is unable to acquire that, because this lock is going to held by some other thread. So a thread cannot acquire the lock in a repeated manner. So that's why this particular condition, which is for X equals to 1 and Y equals to 1, for this minimum value itself, there is a possibility of deadlock. Hence the answer for this question is option D.